This is the review for the Chapter 4 test, and it's really going to focus on what's on the short answer part of the test. So the first problem is from section 4.1, number 47. A bacteria culture contains 1,500 bacteria initially and doubles every hour. Find a function that models the number of bacteria after t hours. If you kind of think about what we did at the very end of the chapter, we had a formula for doubling. It was n of t is equal to n naught times 2 to the t over a, where a was the doubling time. So for this particular equation, n naught is 1,500, and the doubling time is every hour, so a is 1, except what's t over 1? It's just t. So the equation is 1,500 times 2 to the t power. Then we want to find the number of bacteria after 24 hours. So clearly you want to plug in 24 for t. And when I plug that in my calculator, I get a nasty number in scientific notation. I get 2.5165824 times 10 to the 10th. That means I'm going to move the decimal 10 spaces to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 25165824000, which is 25,165,824,000. Problem 53. If $500 is invested at an interest rate of 3.75% compounded quarterly, find the value of the investment after the given number of years. So the formula for compounding anything other than continuously is A equals P, 1 plus R over N to the NT. You will be given a sheet of paper with all the formulas from this unit that you need, and this will be one of them. So, after 1 year, it's going to be 500, 1 plus. You're going to rewrite the rate as 0.0375 over 4, because quarterly means n equals 4, raised to the 4 times 1. And since this is money, you need to remember to round to the nearest hundredths place. That's the nearest penny. You will have $519.02, because you get 0.015, which makes that a 2. After 2 years, you're just going to replace t with 2, so 1 plus 0.0375 over 4 raised to the 4 times 2. And you're going to have $538.75. After 10 years, we're going to do 500, 1 plus 0.0375 over 4 raised to the 4 times 10. And you're going to have $726.23. The next two problems come from section 4.2. The first one is problem 24. A 50-gallon barrel is filled completely with pure water. Salt water with a concentration of 0.3 pounds per gallon is then pumped into the barrel, and the resulting mixture overflows at the same rate. The amount of salt in the barrel at time t is given by Q of t is equal to 15, 1 minus e raised to the negative 0.04 t, where t is measured in minutes, and Q of t is measured in pounds. So think about this. You have this barrel with water, and you're going to pump salt water into it, except that the barrel starts to overflow. Well, when the barrel overflows, some of the salt's going to leave the barrel. It's not all going to stay in the barrel. So, how much salt is in the barrel after 5 minutes? Well, we're going to start by doing 15, 1 minus e to the negative 0.04 times 5. And we're going to say it's about 2.7, and the units of measurement are pounds, or lbs. Now we want to find out how much salt is in the barrel after 10 minutes. So we're going to do 15, 1 minus e to the negative 0.04 times 10. We're going to get approximately 4.9 pounds. Part C says draw a graph of Q of T. Well, I just graphed it in my calculator and I got this. Basically what happened is I had to change my Windows setting. What I want you to know is the graph is going up like this, right? And that kind of levels off. And the reason I want you to notice that is because in Part C, it says use the graph in Part C to determine the value that the amount of salt in the barrel approaches as T becomes large. Is this what you would expect? So we want to figure out what the horizontal asymptote is here, except we're being given an equation that we don't know how to algebraically find the horizontal asymptote to. So another way of determining what the horizontal asymptote is going to be is to go to the table and to watch what happens to the y values as x gets larger. So you can either hold your finger on the button and scroll down and watch the y values, or if you go to second window, you can start your table at different values of x. So maybe do the table start at 50 and then go to your table and see where you're at. At 50 on my calculator, the output is 12.97. And then if I go to my table start second window and I start my table at 100 and then go back to my table, my y value is at 14.725. And then if I go back into my table setup again and I change the table start to 500, because I just keep making it larger and larger, and then I go back to my table, at 500 you'll notice that the y values are all 15. Well, that's kind of interesting because there's a 15 in this equation. Why is it approaching 15? Well, think about this. This part of the equation has a negative exponent. Negative exponents mean reciprocal. So this is really the same as 1 minus 1 over e to the 0.04t. Well, the larger and larger the denominator of this fraction becomes, the smaller and smaller the value of the fraction becomes. So as t gets larger, this is really just approaching 0. And so you have 1 minus 0, which is 1, and then you get 15 times 1, which is 15, which is why we would expect the value of the graph to eventually approach 15 pounds of salt. Problem 31 from the same section. If $2,000 is invested at an interest rate of 3.5% per year compounded continuously, find the value of the investment after the given number of years. Continuous compounding is A equals PE raised to the RT. So if the initial investment is $2,000 and the rate is 3.5%, we're going to plug in 0.035. In this problem, we'll plug in 2 for T. And in this one, we'll plug in 4. And in part C, we'll plug in 12. And then I'll just shove it into my calculator. After 2 years, we'll have $2,145.02. After 4 years, we will have $2,355. And after 12 years, we'll have $3,043.92. In section 4.3, problem number 87 is similar to the one on the test. The age of an ancient artifact can be determined by the amount of radioactive carbon-14 remaining in it. If D0 is the original amount of carbon-14 and D is the amount remaining, then the artifact's age A in years is given by the equation A equals negative 8267 natural log of D over D0. Find the age of an object if the amount D of carbon-14 that remains in the object is 73% of the original amount D0. Well, it doesn't help that they didn't tell me the original amount. That's okay, though. They gave me a sentence that I can write as a little algebraic expression. They said that the amount that remains in the object is 73% of the original. So D is going to be 0.73 D naught. We're going to plug this into this equation in place of D. So we're going to write the age of the artifact is negative 8267 natural log of 0.73 D naught over D naught. These end up canceling, and all you have to do is do negative 8267 natural log of 0.73, and we're going to find out that the artifact is approximately 2,602 years old. Now, it's not that you can't do time in decimals, you can. However, when you're talking about carbon-14 dating, a lot of times the age of the object is in the thousands of years, and we generally round thousands of years to the nearest integer rather than giving a decimal. From section 4.4, number 69, Vilfredo Pareto, 1848 to 1923, observed that most of the wealth of a country is owned by a few members of the population. Pareto's principle is the log of P is equal to the log of C minus K times the log of W, where W is the wealth level, how much money a person has, and P is the number of people in the population having that much money. The first thing we're going to do is we're going to solve Pareto's principle for P using our laws of logarithms. So one of our laws of logarithms says that a number in front of log can get written as the exponent over here. So I'm going to do that first. And then we have a property about subtracting logs. If you are subtracting two logs, you rewrite it as a division problem in this order, C over W raised to the K. And then we have another principle that says if you have two logs equal to each other and they have the same base, they cancel. So Pareto's principle says that the number of people in a population having a certain amount of money is equal to some constant C over the wealth level raised to the K. And C and K are constants. Now that I have that equation, in part B, it says, assume that K is 2.1 and C is 8,000, and W is measured in millions of dollars. Use part A to find the number of people who have 2 million or more dollars. How many people have $10 million or more? All right, so now I'm going to plug these numbers in. So for 2 million, P is going to equal 8,000 divided by 2 raised to the 2.1. And that's going to give me approximately 1,866 people in the population have $2 million or more. Now, if you reason out this problem, you should think that the number of people who have $10 million or more should be less than that. So P is going to equal 8,000 over 10 raised to the 2.1. And in this case, only approximately 64 people have $10 million or more. In section 4.5, the two problems that look like the ones in the test are 75 and 83. 75. A man invests $5,000 in an account that pays 8.5% interest per year compounded quarterly. Find the amount after 3 years. Since it's being compounded quarterly, we're going to use P1 plus R over N to the NT. So he invests $5,000, 1 plus the rate is 0.085, quarterly is 4 times a year, raised to the 4 times 3, and he will have about $6,435.09 in the account. In the next part, how long will it take for the investment to double? So if he starts with 5,000, when he doubles it, he'll have 10,000. So we're going to set 10,000 equal to 5,000, 1 plus 0.085 over 4 raised to the 4t. And then we're going to have to solve this equation for t. So the first thing we'll do is divide by 5,000, and that's going to result in 2. The other thing that I'm going to do is I'm going to simplify what's inside the parentheses. 1 plus 0.085 divided by 4 is 1.02125 raised to the 4t. You can graph this by setting y1 equal to 2 and y2 equal to 1.02125 raised to the 4t. Although this problem is pretty easily done by converting this equation into log form. This equation is an exponential form. If you convert it to log form, it would be log base 1.02125 of 2 is equal to 4t. And then you can simplify this part by either using the base change formula, or if you have a calculator with the log base function, you can do that. If you need to use the base change formula, it would be log 2 over log 1.02125. Please do not forget, if you're going to do this, to close the parentheses. If you don't close the parentheses before you divide, you'll get the wrong answer. So log 2 divided by log of 1.02125 is going to be about 32.964044986. I'm just going to leave that number in my calculator because the last step of the problem is to divide by 4. And then I can get the most exact answer that I can possibly get. I'm going to find out that t is approximately 8.24, and the unit of measurement is years. Problem 83. A small lake is stocked with a certain species of fish. The fish population is modeled by the function p equals 10 over 1 plus 4 e raised to the negative 0.8t, where p is the number of fish in thousands, and t is measured in years since the lake was stocked. Find the fish population after 3 years. So I'm going to plug in 3 for t. Don't forget that they said that p is measured in thousands. That means you have to multiply your answer by 1,000 when you're done. So p is going to be 10 over 1 plus 4e to the negative 0.8 times 4. When you plug this into your calculator, I would put this in an extra set of parentheses. So do 10 divided by parentheses, 1 plus e raised, or 1 plus 4e, I should say, 4 e raised to the negative 0.8 times 4. Of course, I just realized that I said 3 years, and I plugged in a 4 there. I don't know why. So let's try this again. That should be a 3. The answer that the calculator spits out is about 7.337, except we said the p is measured in thousands, so you need to multiply that by 1,000. So the answer is really about 7,307 fish. Then, in part B, it says, after how many years will the fish population reach 5,000? So now we're going to set 5,000 equal to 10 over 1 plus 4e to the negative 0.8t. Now this is a proportion. And so if you cross multiply, you can, because those two are being multiplied and these two are being multiplied, the order in which you multiply doesn't matter. So I'm not actually going to multiply these together. I'm going to write it like this. Because the next step would be to divide by 10,000. So if I divide by 10,000, then this is going to equal to 10 over 5,000, which is 1 over 500. And then I have to subtract 1. So 4e to the negative 0.8t is going to equal 1 over 500 minus 1. 1 over 500 minus 1 is negative 499 over 500. And then I have to divide by 4. Dividing by 4 is the same as multiplying by the reciprocal. So I'm going to get e to the negative 0.8t is equal to negative 499 over 2,000. Now I'm ready to put this in log form. In log form, it's going to be negative 0.8t is equal to the natural log of negative 490. Oh, so that's not going to work, is it? Because I can't take the natural log of a negative. And I figured out why it happened. Go back here. Sorry about that. One of the reasons I like to leave mistakes in the videos is because I want you to see that I do make mistakes. And the key is how you go back and fix them. So now that I come back up here, remember they said P was in thousands. P is not going to be 5,000. P is going to be 5. So 5 is going to equal 10 over 1 plus 4e to the negative 0.8t. I'm going to cross multiply, and I'm going to get 5 times 1 plus 4e to the negative 0.8t is equal to 10. I will divide by 5. So 1 plus 4e to the negative 0.8t is going to equal 2. And then I will subtract 1. And then I will divide by 4. And now I can take the natural log, because I can take the natural log of a positive. And then I'm going to divide that answer by negative 0.8. And I'm going to find out that t is approximately 1.73. And what was it in years? Where t is measured in years since the lake was stocked. So it'll take 1.73 years since it was stocked. From section 4.6, we had 3 problems. Number 9, the population of a certain city was 112,000 in 2006, and the observed doubling time for the population is 18 years. Find an exponential model. N of t is equal to n naught times 2 to the t over a. We'll find for the population t years after 2006. So the population is going to be 112,000 times 2 to the t over 18. In part B, it says find an exponential model, n of t is equal to n naught e to the rt for the population t years after 2006. I gave you a couple ways of doing this. One of the ways of doing this was to just double the population, because we know the doubling time. So you could do 224,000 is equal to 112,000 e to the rate times the time is 18, and then you would solve that for r. So you would have 2 is equal to e to the 18r, so the natural log of 2 is 18r, so you find out it's the natural log of 2 divided by 18. And then you would know the rate. Another way of doing it was to replace the 2 with e to the natural log of 2. So you could do 112,000 e to the natural log of 2 t over 18. And then you would multiply these exponents together, and you should get the exact same decimal that you would if you just do the natural log of 2 over 18, which is 0.0385. So the equation is n of t is equal to 112,000 e to the 0.0385 t. Sketch a graph of the population at time t. You can just do it in your calculator if you want to, but if you notice the rate is positive, so the graph should be going up. And it'll start at like 112,000 and then go up from there. Estimate when the population will reach 500,000. So when will 500,000 equal 112,000 e to the 0.0385t? First, I'm going to divide. And then I'm going to natural log this side. And then I'm going to divide both sides by 0.0385. And I'm going to find out that t is about 39 years. So when will it hit 500,000? Well, 2006 was the starting year plus 39. It's going to be about 2045. Number 23, a wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? The half-life of carbon-14 is 5,730 years. Since this is a half-life problem, we had an equation for half-life. It was this, where the rate is the natural log of 2 divided by the half-life. So the easiest way to find the rate is to do the natural log of 2 divided by 5730, which we found out was 0.000121. That is always the rate of decay of carbon-14. Now, they didn't give me the original amount, did they? But I do know that the new amount is 65% of the original. So I'm going to plug this in for m. 0.65 m naught is going to equal m naught e to the negative 0.000121 t. These go away. I can natural log the other side. And then I'm going to take the natural log of 0.65 and divide it by negative 0.000121. And I'm going to find out that my object is approximately 3,560 years old. The last problem. The Alaskan earthquake of 1964 has a magnitude of 8.6 on the Richter scale. How many times more intense was this than the 1906 San Francisco earthquake? And then it says see exercise 36. So in exercise 36 it says San Francisco earthquake in 1906 had a magnitude of 8.3 on the Richter scale. We did a problem like this where we had the magnitude was equal to the log of the intensity over S was like if there was nothing shaking at all. And we rewrote this in exponential form, since this was a common logarithm. We rewrote it as 10 raised to the magnitude is your intensity. To figure out how many more times one earthquake's intensity is than another, you're going to divide their intensities. You put the bigger one on top. So we're going to do 10 raised to the 8.6, in the numerator, and 10 raised to the 8.3 in the denominator. And then we're going to divide those, and that's going to tell us how many more times intense one earthquake is than the other. And it's like 1.995, so we're going to say it's about 2 times as intense. The multiple choice part of this test is going to be a little bit more skills-based. So my recommendation is to go back over some of the skills-based problems we did in the unit. All the formulas that you're going to need will be given to you on a formula sheet. If you have any questions about this or any problem on the test, please email me.